All right, guys, in this video, we're going to do the review for the BC test that covers sections 6, 7, and 8. So this first one says, given that y of 1 is equal to -3 and the differential equation 2x plus y, what is the approximation for y of 2 if Euler's method, we'll call it Euler's method, is used with a step size of 0.5 and you start at 1. All right, so we drew this little table, and I think if you memorize this table, it's going to be really helpful. And we say it says x, y, y prime, and then new y. And the way we get the new y is we take the old y and we add the rate of change times delta x, like how the x is changing. So if we start at 1 and we need to approximate the value at 2, I'm going up by 0.5 because it says step size is 0.5. So I have to do a couple rows. So the y that goes with that first x is -3. Y prime, you get y prime by plugging your x and y into the derivative. That tells you the slope, or y prime. So 2 times 1 is 2, minus 3, so that's -1. So to find my new y, I take the y that was there, and then we add the rate of change, which is -1 times the change in x, 0.5. And that would give us -3.5. That becomes your next y at your new point. That's an approximation. But I want to find this number right here. So I got to do one more step. All right, to find y prime, I take this x and y, and I plug it into the derivative to find me the slope there. So 2 times x, 2 times 1.5 is 3. And then 3 minus 3.5 is -0.5. To find the new y, I take that y. I add the change in y, which was negative, times you change in x. And if I get that, I get -3.75. And that would be our answer. So I would say y of 2 is approximately, because Euler's method just approximates, -3.75. All right, so this would be another one. You could try it on your own and then pause the video and then come back and see if you got it right. So it says, let f of x equal y be the particular solution to this differential equation. So the differential equation is new, or is it the same? A little different. With the initial condition of f of 0 is equal to 1. So if I plug in 0, I get 1. Use Euler's method starting at 0 with 2 step sizes, or 2 steps of equal size to approximate f of -0.6. So this time it doesn't tell you what the step size is. You can kind of figure that out. It's an extra step. But still, it's x, y, y prime, new y. The first point that we're given is 0, 1, but I want to go backwards to -0.6. So just 2 steps of -0.3, then -0.6. Now I fill out my little chart. So if I plug in 0 for x and 1 for y to my differential equation, I get the slope is 2. To find the new y, I'm going backwards. So, well, yeah, I guess I'm going back in the x direction, but still. So the new y is the old y plus the y prime times delta x, which is -0.3 this time. I'm going back -0.3, back -0.3. That delta x is going to be the same every time, if you remember that pattern. All right, so get that would give us 0.4. Bring down 0.4. To find y prime here, plug in x is -0.3 times 2 times 0.4, and that will give me 0.5. To find the new y, it's the old y, plus y prime times delta x, which is still -0.3. And that gives me 3.85. I did that earlier in the calculator. All right, so that would be the answer. F of -0.6, is approximately 3.85. Next, calculator active. Says the derivative is sine of e to the x, and f of 0 is 5.7, and f of 2, we want to find f of 2. Okay, this is not technically like a BC Unit 6, 7, 8. What this is just fundamental theorem of calculus. And I just want to show you it as often as possible so you can kind of recognize it, because it is the fundamental theorem of calculus. So I know if I integrate the derivative function or a function from a to b, that is equal to the antiderivative of this integrand, so f evaluated at b minus f evaluated at a. So I'm using that property to know that the integral of sine of e dx, which you don't have to find, it's calculator active, and my limits of integration will be from 0 to 2, because I'm given 0, f of 0, and I want to find f of 2. This is equal to, we'll say this is, if this is f prime, then the antiderivative, we'll just call it, it's f of 0 or f of 2 minus 5.7, the bottom one, right? All right, so this part is done in the calculator, so it's calculator active. You plug it in. I plugged it in earlier. I got 0.550935 is equal to f of 2 minus 5.7. Add 5.7 to both sides, and you get 6.25094. So calculator active because of this part. Fundamental theorem calculus, don't forget it. All right, number 4 is going to be my favorite problem in this whole review because it's just terrible. It's just not fun. This is an improper integral. I shouldn't have told you that already. So we're supposed to look at it and we think, okay, I have to find the antiderivative of this evaluated from 11 to 2. So the area under that curve from 11 to 2, it's not calculator active though. So if I was to graph this, I'm going to have a vertical asymptote. And without graphing this, we have to do this without being able to see a graph. So we have to know if I rewrite this as a positive exponent, that this whole part becomes like the bottom. So now I look at it and I got to know, okay, there's a vertical asymptote at when x is 3. Because if I plug in 3, it makes the bottom 0. And there's a definition of vertical asymptote. So as my graph the x's get closer to 3, the y values either get infinitely huge or infinitely small. Depends on what side of your 3 you're coming from. This one would be square, so it wouldn't really matter. But anyways, so 3 is a problem because it's within 11 and 2. If it wasn't within that interval, it wouldn't matter. We could just continue like normal. But it does matter. So I'm going to have to rewrite this limit, or this integral. I'm going to break it up into 2 parts. The integral from 2 to 3, 1 over x minus 3 to the power 2/3 dx, plus the integral from 3 to 11, same thing, integrand, 2/3 dx. It's a 1. Okay. So that's great, but now this is called an improper integral because we are finding the area of an unbounded curve. Okay, I don't know what this looks like exactly, but here's 3, and my graph might look like that. So this area is unbounded. It just keeps going up forever, right? Even though it stops like over here at 11. It's unbounded for that region. So we have to make this a limit question. Because I can't actually plug in 3. But what I can do is I'm going to replace these 3's with dummy letters. And I'll say this is the limit. As a approaches 3, okay, which way? From the left or right? So here's 2 to 3. It's approaching from that way. So from the left of the integral 2 to a 1 over x minus 3 to the 2/3 dx plus the limit as b goes to 3 from the right, this time b's down here, to 11, 1 over x minus 3 to the 2/3 dx. All right, so now we find the antiderivative. Oops, I erase that. The antiderivative of this, I might turn it back into the x minus 3 to the negative 2/3 and just reverse power rule. U is x minus 3, but du is just 1. So it's a u sub problem, but not really, I guess, or that's an easy one. So add 1 to the exponent. Adding 1 to 2/3 is 1/3. Multiplied by the reciprocal, that would be 3. And then keep the inside part, x minus 3. We evaluate that from 2 to a. And the whole time we're talking about limit as a goes to 3 from the left. These little dots. Plus, same thing over here. Don't have to redo the integral. It's the same integral. 3x minus 3 to the 1/3. Evaluated from b to 11 this time. All right, running out of room. Oops. All right, so, okay, now we gotta plug in the limit as a approaches 3 from the left of, okay, now we plug in a, 3a minus 3 to the 1/3 minus, now plug in 2. 2 minus 3 is negative 1 to the 1/3. This is like a cube root. Exponent 1/3 is cube root. Okay, I'm gonna add this to the limit as b approaches 3 from the right of 11 minus 3, 1/3 minus, now plug in b. So long problem, not each step isn't terrible, but altogether you gotta know what to do in the next step and it just kind of gets a little tedious. All right, now the limit as a approaches 3. Okay, as I plug in numbers really close to 3, smaller than 3, it's like 2.99999. Minus 3 is basically 0. Cube root of 0 is 0. 0 times 3, I'm just gonna call that 0. Okay, cube root of negative 1 is negative 1 times negative 3, so plus 3. I'm going to add the limit over here, so 11 minus 3 is 8, cube root of 8 is 2, 2 times 3 is 6. And the same thing here, plug in numbers just bigger than 3. That's basically approaching 0. Okay, so plus 0. So the answer is just 9. I think that was the tough one. In my opinion, that was the kind of longest drawn out question. All right, next one. Okay, I made this one a multiple choice because, oh no, I don't know what I'm saying. If I see this natural log, I think integration, all right, function composition, partial fraction decomposition, that's what I'm going for. But then there's arctangent stuff, so I'm like, wait, arctangent is like the integral of 1 over u squared plus a squared dx, or du, I guess. This would be like 1 over a tangent inverse of u over a plus c. So that kind of tells me, okay, I think when I get arctangent, the bottom has to usually be like an x squared plus another number. That's usually perfect square. It doesn't have to be. So I'm thinking, okay, well, that's not like this now. Can I factor that? If I could factor, I could do the a over factor plus b over factor. But I don't think this can even be factored. Two numbers that multiply get positive, I have to give negative 10. No, it can be factored. So, this is kind of the thought process I'm doing as I'm thinking about these questions. I'm going to try to complete the square here. To complete the square, we're just rewriting this trinomial as something that can be factored into the perfect square. So I'm going to say minus 10x plus 34. I'm going to kind of leave a little space to complete the square. The rule is take half of this number, which is negative 5, and square it. So adding 25 here and subtracting 25 here keeps this value the same. Doesn't change the value of the bottom, but it changes the way it can be written. This would be x minus 5 squared plus 9. I think that's right, plus 9. Okay, yeah. So now I've got that form where this is like the u squared part, this is the a squared part. So I could say u is x minus 5, du is just 1, and then a would be 3. So I don't know why I erased that thing earlier, but I think the answer would be C. And that's just knowing that tangent inverse. So I originally said you don't really need to know that, but let's just know that. The integral of 1 over something plus something, the squares, is that tangent inverse one. I think you can work from there. Just one other thing, arctangent, remember the same thing as tangent inverse. All right, next one. All right, this one, the bottom's already factored for us. That's nice. If you tried u sub, it wouldn't work. If you make the whole bottom u, du would be like 2x, there's no other x term. So if I can factor the bottom, I'm gonna try to rewrite this fraction as two separate fractions. So I'm gonna rewrite this as, I'm just looking at the fraction part, not looking at the integral. Rewriting that fraction as a over x minus 1 plus b over x plus 2. Doing some algebra, multiply everything by x minus 1, x plus 2. And you might have started skipping the step at some point. But I'm doing this partial fraction decomposition when the bottom can be factored. All right, so now the fun part, cancel, 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 cancel. I've got 3 is equal to a times x plus 2 plus b times x minus 1. Now when I get a, the value of a, I plug it back into this fraction right here. So okay, that's all I'm gonna say. Yeah, plug it in there. I sometimes plug it in here and mess it all up as I'm slow. Okay, x is equal to the negative 2, plug that in. If you plug in negative 2, this thing cancels out, that whole a term. So I've got 3 is equal to a times 0 plus b times negative 2 minus 1 is negative 3. So b is negative 1. If I plugged in what makes this 0, which is 1, I'd have 3 is equal to plug in 1 right here. This would be a times 3, and this is 0. So a is 1. So whatever those numbers are, like if they're 1, it's kind of like, you kind of like lose track of them. But whatever number that is, put that number over that fraction. So now I'm going to say the integral, my original equation, or my original integral, that whole thing is equal to the a number over x minus 1, this. I got 1 for the a, so it's the integral of this, over x minus 1 dx. Plus the integral of the b over x plus 2, and b was negative 1 dx. Okay, this is nice because now we usually take this number, we put it in front. So this would be like just 1. Okay, this is obvious, okay. But if there was a number there, like number, I say number integral 1 over x minus 1, and then it's just the natural log with the number in front. Okay, but this one, it would just be the natural log of x minus 1 with that 1 in front, but you don't need it. But this negative makes that minus, so minus the natural log of x plus 2, and don't forget the plus c. Multiple choice, I'll have the plus c there to kind of remind you, but if this is FRQ, make sure you put the plus c. If you don't have that constant of integration, you get it wrong. And the constant of integration is only needed when you don't have numbers for the limits of integration. All right. Number 7, letter 7. Oh gosh. Okay. Wouldn't do partial fraction decomposition because it's not a fraction. I wouldn't complete this square because there's no like polynomial that can rewrite it as a perfect square. This one, I've got a function times another function. Okay, I don't really remember this formula. The integral of u dv is uv minus v du. You could do it that way, but this tabular method is so nice, and it usually works. We talked about when it doesn't work, when it does work. So I put plus, minus, and then the derivative term. So if these two things are being multiplied together, I know I can do integration by parts. If I take the derivative repeatedly and it eventually goes away. The antiderivative of e to the x is e to the x, e to the x, e to the x, that's nice. And then we gotta go over, down. And then over, down. Don't do blue, what is that gonna look like? Oh, it kind of shows up. All right, so I would do positive x squared times e to the x. Negative 2x times e to the x. Positive 2 times negative, or times positive e to the x. So plus 2 e to the x. And then don't forget your plus c. And that'd be it. All right, number 8. By the way, number 18 is got some, I don't know, I'm telling you this now, but if I forget, it's got some typos on it. So we got to make sure we talk about number 18. Okay, number 8, which of the following statements about the integral that is true? Okay. Well, it looks pretty basic if you like. I'm just looking at it on the surface level. Like, okay, yeah. Rewrite this as negative 2. There's your limits of integration. Add 1 to the exponent. Multiply by the reciprocal. Plug in negative 1. Plug in 1. And if you're not being super careful, it's negative 1 over 1 minus negative 1 over negative 1. Oh gosh, that's a lot of negatives. I'm going to confuse myself. This is probably going to be wrong. But you get the idea. So it's -1 minus 1, so -2. People pick A. That's going to be wrong. Okay, the reason this is wrong is because if you look carefully, is there a vertical asymptote for this graph? And you're like, how am I supposed to know that? Okay, if there's an x that makes the bottom 0, that is a vertical asymptote if that restriction doesn't cancel on top. Like if there's an x on top, they cancel, it becomes a hole. That's algebra 2 stuff. Okay, but the restriction does not cancel. That value of x is 0, that's going to be a problem. And 0 is within your limits of integration. So we have an improper integral. We have an area of an unbounded region. So we need limits with infinities like this. So I'm going to rewrite this like we did that other one. I think it was like number 3. -1 to a of 1 over x squared dx, and it's the limit as a approaches 0. And you can say from the left, plus the limit as b approaches 0 from the right, from b to 1 over x squared dx. And I'm pretty sure it's not a. Oh gosh, no, I think we're gonna start arguing about it being b. No, it's not b. It's not b. Some of y'all are like remembering if there's a positive infinity and negative infinity area, don't those just cancel out? But these will both be positive, so we'll carry there. Otherwise, it's a little debatable. Okay, so this would be, I'm gonna rewrite this as x to the -2. Add 1 to the exponent, I've already forgotten what it was. Okay, so the limit as a approaches 0 from the left, antiderivative, we said, what was it? Add 1, negative x to the -1. So -1 over x. Evaluated from -1 to a, plus the limit b approaches 0 from the right. Same thing, but you say b to 1. All right, so now if I plug in a here, what's the limit as a approaches 0 from the left of -1 over a minus a -1 over -1? As a approaches 0, can you divide by 0? That's pretty much undefined, right? The other idea is as a approaches 0, this bottom is getting infinitely small. Tiny, tiny, tiny. And if I've got 1 divided by a tiny number, that overall number is huge, so it approaches infinity. So I'm going to say the limit as a approaches 0 of that limit doesn't exist because it's infinity. So that would be our reason. It diverges because that limit doesn't approach a number. It just keeps getting bigger and bigger and bigger without bound. That idea of integral diverges means it's not adding up to a number. It just keeps getting bigger and bigger and bigger, so it's diverging. All right, number 9. Hopefully you see this. You're like, oh, multiplication. I would try USUB. Wait, USUB doesn't work, so I've got other little tools. Integration by parts. Tab it out. So plus minus x squared 2x to 0. The integral of sine, be careful, is negative cosine, because the derivative of cosine is negative sine. So the integral will be negative cosine, right? Derivative of, yeah, that's right. And then negative sine, and then cosine. Over and down. So multiplying that together, you got negative x squared cosine of x. Two negatives would be plus 2x sine x plus 2 cosine of x plus c. All right, now number 10, getting there. Number 10, I'm going to try to factor the bottom, or I'm going to complete the square to make it a perfect square trinomial. Can I factor that? I think I can factor it. It's 1 over x plus 2, x plus 4. So I'm going to rewrite that fraction as a over, I wrote 4, I said 4, wrote 2, over x plus 2 plus b over x plus 4. Just rewriting this as two separate fractions, because then I know the integral of that would just be natural logs. All right, so, okay, be careful. Okay, I almost forgot. Sometimes there's like a 3 down here. So if you were integrating this, be super careful that u is 3x plus 2, du would be 3, so there'd be an extra 1/3, and then the a out there also. I really kind of did a bad job explaining that. I don't know if I did some examples like that. Who knows? Who cares? All right, so what are we doing? Oh yeah. Get rid of the denominator. So I go with this 1 is a times x plus 4 plus b times x plus 2. Plug in x is -2. If I plug in -2, that b term goes away. Plug in -2 right there, I get 2. So a is 1/2. Okay, if I plug in, oh wait, did I say that right? Did I say plug in -2? Just a second. X plus 2, so b x plus 4. All right, if I plug in okay, we're good. Plug in -4. Plugging in -4, I get 1 is equal to, the a term would cancel, and the b would be, the b part, -4 plus 2 is -2. So b is -1/2. Okay, on my notes, I think I did this wrong. Oh, I just called a different. Okay, so we're good. Just double checking something. B. Okay, so on my notes, when I did this earlier, I just happened to write the x plus 4 first and the x plus 2 second. So the value I get for a and b would be switched, but this b number, the -1/2, still goes over the x plus 4. So when I got a was -1/2, a was over the x plus 4. So it just kind of works out. Don't have to worry about that. Okay, so this would be equal to the integral of the a number, which is 1/2 over x plus 2 dx. I'm going to put the 1/2 out in front, just a 1 here. And the b number is negative, so it'd be -1/2, 1 over x plus 4 dx. Integrate all this, it would give me 1/2 natural log of x plus 2 minus 1/2 natural log of x plus 4 plus c. When you are integrating, be careful, make sure that is, like if you have to do u sub, like if there was a 3 here, to make up for the extra factor of 3 in the du, it would be 1/3 multiplied out here. So this would be 1/6. So just, yeah. Hopefully you're watching this and remember that someday if it comes up. All right, number 11 looks like an improper integral. This one's pretty obvious because the integral, or the limit of integration is infinity, so it's an unbounded region. It goes on forever. There's no like stopping point, but it still could converge. So I recognize this is, well, I'm gonna write this as the limit as a goes to infinity of the integral from 0 to a 1 over 9 plus x squared dx. I recognize that the antiderivative of this is tangent inverse of x over 3 1/3, because you know that little formula. And this is the limit as a goes to infinity. You evaluate from 0 to a. This might go out here, looks a little better. All right, now plug in a 1/3 tangent inverse of a over 3 minus 1/3 tangent inverse of 0 over 3. Just plug in the lower limit of integration. Limit the whole time. All right, this part, tangent of 0 is just 0. So it's minus 0. You have to know this graph. Those are asymptotes. Goes up to positive pi over 2 to negative pi over 2. That's tangent inverse. So the limit as I plug in huge tangent or huge values of a, even though if I divide them by 3, they still get huger, huger, huger. So the limit of this, well, limit of this part is just pi over 2. But it's 1/3 of that because it's 1/3 right here. So this would be pi over 6. Answer. So it converges. If I got the limit was infinity, then the limit diverges. All right, number 12. How long this video's been going on for? Number 12, the number of people, so differential equations. Logistical growth. The number of people in a store is modeled by this function. So I guess there's only so many people that can fit in the store. Remember, the whole idea behind logistical growth is it grows and it levels off. There's a maximum carrying capacity that this population can hold. Whatever this limit is, halfway through, the growth rate is at the highest. So if this is 100, this is at 50, but it's when y is 50. The t numbers could be a little bit different. All right, so this derivative tells you how that gives you the slopes of those moments. That graph is from the general solution. Okay. Anyways, what is this question even about? Okay, there's an equation. I like it. Okay, it's got this little play of, it's got an f outside the parentheses. That's, if I plug in bigger f's, it gets bigger. And then there's this play inside where if I plug in bigger f's, it gets smaller. And that kind of as one gets bigger, one gets smaller, kind of plays it off, and that's how it does that mess. Okay, where if I plug in 0 times 0, I get 10. What's the greatest rate of change in people per hour of the number of people in the store? All right, so the greatest rate of change in people per hour. So that's this number, right? Of the people, what is the greatest rate of change? Rate of change, that's the derivative. People per hour, the number of people in the store. Okay, the carrying capacity is 100. So that means if I go back a step, it would be, or half of that is 50. So when f is 50, that's when the growth rate is the highest. If f is 100, that's the limiting capacity. So if I want to find, it's not just asking for this number, it's wanting to know what is the rate so we know the greatest rate happens when f is 50. Now it wants to find the actual number. So 1 over 500 times 50 times 100 minus 50. Plug this into, or I didn't plug this into the calculator. This is 50. And then this is 50. This is 1 over 500. So 50 times 50 is 2500 over 500. Cancels. And the 25 divided by 5 would just be 5. All right, so, and that is people per hour. People per hour. All right, number 13, find an integral that is equal to the length of the curve from points 0,1 to 249. Don't evaluate. Okay, this is arc length. It doesn't tell you arc length, but this is arc length. You have to know the formula for arc length, it's called S, is equal to the integral from A to B, square root 1 plus the derivative squared with respect to x, so dx. So in this one, I'm going to go from 0 to 2. So S is the integral from 0 to 2 square root 1 plus the derivative. So something, don't forget to square it. Because the derivative would be 12x cubed plus 2x minus 2. Then that would be it. You could square that out, whatever, but there's an integral that would set it up. All right, number 14, the length of the curve is that from 0 to 1. Okay, so same thing, set it up from 0 to 5, so from 1 to 5. Okay, this is y, so y prime is 6x squared. Be the integral from 1 to 5, square root 1 plus this squared. So 36x to the 4th dx, so this one. All right. No calculator for number 15. Consider this function, evaluate that indefinite integral, so improper integral. All right, so this one has got got two ideas. It's got this limit as a approaches infinity, the integral from 0 to a f of x dx. But f of x is all this. So I need to find so to integrate that, the antiderivative is an integration by parts. Plus, minus, derivative integrals, plus, minus, plus. x, 1, 0, e to the negative 2x. Come on. The antiderivative of that would be a u sub, so u is equal to negative 2x, so du is negative 2. To counter out the negative 2, I say negative 1/2, e to the negative 2x. Then negative 1/2 times negative 1/2 would be 1/4, e to the negative 2x. Over, down. So this would be the limit as a approaches infinity of, let's see, negative 1/2 x e to the negative 2x minus 1/4 e to the negative 2x, all evaluated from from 0 to a. All right, so plug in a, limit as a approaches infinity. This would be negative 1/2 a e to the, I'm going to say this is going to be 1 over e to the 2a minus 1/4 1 over e to the 2a. That's when I could plug in a. If I plug in 0, so minus, okay, 0 times that wipes that one out. Negative 1/4 e to the 0 is just 1. So it would be that. All right, limit as a approaches infinity. As this gets, okay, plug in a up here. Let's do a up here. Okay, as a gets huge, we could do L'Hopital's rule here, really, because in this one, as a approaches infinity, I have infinity over infinity. But I could also see that as a approaches infinity on the bottom, it's growing much faster. So if I took the derivative of the top, I get 1 over, and this would be e to the 2a still. So as a approaches infinity, this whole thing is approaching 0. Because this is approaching infinity, right? Getting huge. Overall, that's approaching 0. So 0 minus 0 is 0. Minus a negative 1/4 would be 1/4. Final answer. I would do one more question here. I'll do these questions, the FRQ style questions, as a separate video because I'm going to run out of time. Okay, set up an integral to represent the length of the curve on that interval for a function defined by this. And you're like, wait, there's already an integral here. But part of the, what is it called? Arc length formula. Is this the integral from a to b? In this case, it would be from 2 to 5. 2 to 5. Square root 1 plus the derivative squared. The derivative of y. Well, the derivative of this means take the derivative of this, and that's an accumulation function, where I just plug in x here. Oh, crap. This should be a t. I typed this wrong. That should be a t. Those can't be the same letters. So plug in x in here, and it would just be, the derivative is just x to the 4th plus 3 squared. That is the derivative. That squared would be the integral setup. So okay, I gotta reset that. Y prime is equal to, this function up here should have been the integral of 1 to x t to the 4th plus 3 squared dt. So the derivative of that just plugs in here. So y prime is x to the 4th plus 3 squared. But the formula says take the derivative, and then on top of that, square that. So I could probably rewrite this even as just say that would be a 4. All right, that's it for this part. I'll do a separate video probably during lunch to show you the FRQs. You don't care when I'm doing this. Okay, it'll be posted in another one. Thanks for watching. Hopefully this helps, and just keep working really hard. I'm proud of you. Bye.